Hi everyone, welcome back to my YouTube channel, and in today's video we will learn DFS approach to arrange the nodes in topological order. So to perform the DFS algorithm we need two main tools. So first one is this visited array to keep track of nodes that we have already visited or the nodes that we have already processed, and the second one is stack data structures to store the nodes in topological order. As we all know, stack operates on the principle of last in first out, which means a node which has been inserted last in the stack would be taken out first. So the code intuition of this DFS algorithm is very simple. What we are going to do is we will make a DFS call for every node in the graph, and we will push a node into the stack only if its DFS call has been completely finished. For example, if I consider this node 0, we will push it inside the stack only if all the nodes that are reachable from 0 are already processed and are sitting inside the stack. So let us understand this algorithm by doing a drawing run. So we are going to initialize this visited array with 0 because initially all the nodes are unvisited. Okay, so first we will make a DFS call to 0, and here I am also drawing the adjacency list. Okay, so I will write the neighboring nodes of 0. So since 0 does not have any adjacent nodes, so adjacency list for 0 will be empty. 1 has two adjacent nodes, 0 and 5. 2 has two adjacent nodes, 0 and 3. 3 has one adjacent node, 4. 4 has one adjacent node, 5. And 5 does not have any adjacent node. Okay. So first we are going to make a DFS call for 0. Okay. So when we make a DFS call for 0, we will mark 0 as visited, indicating that we have processed 0. Now we will explore the neighboring nodes or adjacent nodes of 0. So we will look into the adjacency list. 0 does not has any adjacent node. Okay, so we have done all the work for 0 and all the nodes that are reachable from 0 are processed. So we will simply return from the DFS call, but before returning we will push 0 inside the stack, indicating that 0 has been processed fully and we can simply push it inside the stack. Okay. So now we will make a DFS call for 1. Okay, and we will mark 1 as visited. Okay, now we will explore the adjacent nodes of 1. So 1 has two adjacent nodes. First one is 0 and second one is 5. So 0 is already visited, hence we will not make a DFS call for 0. 5 is not visited, hence we will make a DFS call for 5. Okay, and we will mark 5 as visited. Now we will explore the adjacent nodes of 5. As we can see in the adjacency list that 5 does not have any adjacent nodes, so we will simply return from this DFS call to back to 1, but before returning we will push 5 into the stack. indicating that we have finished the DFS call for 5 and all the work for 5 has been done completely, and means all the nodes that are reachable from 5 has already been processed. Okay, so now since we have returned from the DFS call for 5, we have returned back to 1. Okay, now all the adjacent nodes of 1 are processed, that is 0 and 5 both are processed. Okay, which means we have completed all the work for 1 and we can simply return from the DFS call 1. But before returning, we will push 1 inside the stack. Okay, indicating we have done all the work for 1. Now we will make a DFS call for 2 and mark 2 as visited. Okay, now we are going to process the adjacent nodes of 2 that are 0 and 3. Since 0 is already visited, we will not make a DFS call for 0. 3 is unvisited. Okay, so now we will make a DFS call for 3 and mark 3 as visited. Okay, so now we will process the adjacent nodes of 3. Okay, 3 has one adjacent node, that is 4. So we will make a DFS call for 4 and mark 4 as visited. Now we will process the adjacent nodes of 4. So 4 has one adjacent node, that is 5. But 5 is already visited. Hence, we will not make a DFS call for 5, and as we can see, all the adjacent nodes of 4 has already been processed. So we can simply return from the DFS call for 4, and before returning, we will push 4 inside the stack. Now we have returned back to 3, and as we can see, all the neighboring nodes of 3 are already processed, are already visited, which means we have completed all the work for node 3. So we can simply return from DFS call for 3, and before returning, we will push 3 inside the stack. Now we will return back from DFS call for 3 to 2. As we can see here, for 2, we have already processed all the neighboring nodes of 2. Both 0 and 3 are already processed, which means we have completed the work for 2, and all the nodes that are reachable from 2 are already sitting inside the stack. So we have completed the work for 2, and we can simply return from DFS call for 2. And before returning, we will simply push 2 inside the stack. So finally, this is our topological order. Okay. We can also cross-check our answer. Okay, let us first write down all the directed edges in our graph. If I consider this first directed edge 2 to 0, so 2 always appears before 0 in this order, hence the first edge is verified. Okay, if I consider 1 to 0, so 1 appears before 0, hence second edge is also verified. If I consider this directed as 2 to 3, 2 appears before 3, hence this is also verified. And if I consider this directed as 3 to 4, 3 also appears before 4, hence this edge is also verified. And if I consider this directed as 4 to 5, 4 also appears before 5, hence this edge is also verified. And if I consider the last edge 1 to 5, 1 appears before 5 in this order, hence this edge is also verified. Now we will understand the code for it. So here I have created an adjacency list. So in this question, we were given a list of directed edges. So from the directed edges, I have created an adjacency list, and I have also created a visited array to keep track of nodes that we have already visited, and a stack data structure to store the nodes in topological order. Okay, so here what we will do is we will make a DFS call for every node in the graph if it is not visited. Okay. And in the DFS call, we will pass the node for which we are making the DFS call, and we will also pass the adjacency list, and we will also pass a visited array and the stack data structure to store the nodes in topological order. Okay. So when we make a DFS call for a particular node, we will first mark it as visited, indicating that we have processed this particular node, and then we will explore the neighboring nodes for the current node. And we will make the DFS call for its neighboring nodes only if the neighboring nodes are unvisited. Okay. So once we have processed all the neighboring nodes for the current node, which means all the nodes that are reachable from the current node are processed, we can simply push the current node into the stack, indicating we have done all the work for current node. So once we have completed the DFS call for all the nodes, the stack data structure will store the nodes in topological order. So we will store the nodes in our answer vector, and we will simply return the answer vector. So yes, that's all about DFS approach to arrange the nodes in topological order. Thank you so much. And in next video, we will